So the next speaker is Mitchell Harris, and the title is Improved Non-Negativity Certification with Bernstein Polynomials.
Today I'm going to be talking about a new certificate of positivity or non-negativity on an interval. It's joint work with my advisor, Pablo Brillo. So the goal of today's talk is to prove that a polynomial is non-negative using the Bernstein basis. We present a new technique that is better than existing techniques that just use the Bernstein polynomial basis coefficients. And then we generalize this to matrix-valued polynomials of arbitrary degree. So the schedule for the talk is to first discuss Bernstein polynomials. I'll give you guys an introduction, definition, nice properties that foreshadow how it's used in practice. And then I'm going to talk about the simplest setting that our result makes sense in, which is the cubic univariate scalar polynomial. Then we'll talk about arbitrary degree matrix polynomials using natural generalization of the same technique. And then we'll look at some numerical experiments of how it does in practice on some simple examples. So the first line of this slide is the definition for the Bernstein polynomial, the ith Bernstein polynomial of degree n. We're going to focus mostly on the n equals 3 case, just because non-trivial things start to happen. And so I've explicitly written down the n equals 3 case of the first line right below that. There are three very important properties of the Bernstein basis. The first is it's a basis of the degree of the polynomials. It's also non-negative on the interval from 0, 1, which is obvious from looking at each of them individually. They're all factors x and 1 minus x. And finally, they're a partition of unity. That is, that if you sum them for any fixed x, you get 1. There are many other properties, but those are the three that we're going to make use of. So here I've plotted a cubic polynomial, which is pretty simple. It just looks like any other cubic polynomial. But I want to somehow incorporate the Bernstein coefficients, so the coefficients of the Bernstein polynomial basis, into this plot. So we can use what are called the control points of the polynomial. Instead of thinking of it as just a curve, we think of it as a parametric curve. Instead of y equals f of x, it's the curve x p of x. X has a constant decomposition in the Bernstein basis with Bernstein coefficients 0, 1/3, 2/3, and 1. So it makes sense to put these points on the graph that we had before. Then I connected the 4 points to form the convex hull of those 4 control points. The most obvious thing that you might recognize is that the curve or the graph lies inside of this convex hull of control points. And this is a very well-known, very famous theorem that I'm going to prove just because it's very related to the baseline that we're going to compare our method to. And it's also just like a 2-line proof. So the theorem is that any Bernstein polynomial, the graph of the Bernstein polynomial is contained in the convex hull of its control points. So we can write x px by definition of x and px as this sum where the coefficients are bix times control points. But remember, 2 of the 3 properties were that the bix are non-negative and that they sum to 1. So then xpx is a convex combination of the control points. And so xpx lies in the convex hull. Now the corollary is actually the thing that we're going to use directly, which is that a polynomial is lower bounded by the coefficient, the smallest coefficient in the Bernstein basis. okay, there are many applications of Bernstein polynomials, but what I discussed is sort of the route that we're going to take and how we're going to use them. But then the applications of this method might apply to any of the applications that you might use a Bernstein polynomial for. So now let's talk about what exactly the question that we're solving precisely in, like I said, the simplest setting. So again, these are the Bernstein polynomials. And our question is to give conditions on these coefficients that imply that for every x in the unit interval, the polynomial is non-negative. So for the rest of the talk, I'm just going to use pi to refer to the p0, p1, p2, p3. If there's a p, then you can assume that the pi are the control points or Bernstein coefficients. I'll say those words somewhat interchangeably. And even though when I say control point, usually I'm referring to just the p, not the constant coefficients that will refer to x. And if I say pi, then there's a p in the background. So this question is, very fundamental. There are a spectrum of answers that people have given. We're going to sort of compare to just two of them. So on the one hand, you can have an exact, maybe expensive second-order cone or semi-definite program. So in the cubic case, it's not really that expensive. People do this all the time. But you can compare this. So p is positive polynomials. So I'm going to use the curly p everywhere to mean positive on the interval 0, 1. So I don't have to say positive on the interval 0, 1. So a polynomial is in p if it's non-negative on the interval. And on the other hand, we might want a cheap condition, something that's that doesn't quite capture the whole set of positive polynomials, but it approximates the set from the inside. So if this condition is satisfied, then we know that our polynomial is positive. And so the proof that every polynomial with positive or non-negative control points is non-negative follows from that corollary from before, which said that a polynomial is bounded below by the smallest control point. So if the smallest one is bigger than 0, then the polynomial itself is bigger than 0. This is very classical stuff. A lot of you probably have seen this before. But so the question that we thought about is there something in the middle? Or maybe even does a better balance of the trade-offs of a cheaper condition, but closer to capturing the full set of positive polynomials? So remember the pi bigger than 0, or you might notice that to enforce this condition in like an optimization problem, it's just a linear condition. Which is much less expensive than, especially for higher degree semi-definite programming certification for a high degree polynomial. Okay, so this example, I'm going to show just a little motivation for what's kind of wrong with this set NB. Oh, by the way, NB, we named it that. I mean, it's an existing set, but we use the name NB to mean non-negative Bernstein. So you can remember what the set means, NB, non-negative Bernstein, the coefficients are non-negative. So what's wrong with NB sort of visually if you just look at a cubic polynomial? So this polynomial is non-negative, right? The blue curve. And you can prove it's non-negative by looking at the bounding box, seeing that the y-coordinate of the smallest control point is 0, so the polynomial is always bigger than 0. But what if we perturb that control point just a little bit, going from 0 times b2x to negative 1 times b2x? Then the bounding box no longer gives you any certificate, but this polynomial is clearly positive. So we want a condition that's less sensitive to these sort of perturbations of the values of the coefficients. And so here we go with our condition in the cubic case. Let's define x plus to be the maximum of x in 0. So this is the projection onto the positive orthant or non-negative orthant of x. And then we're going to define P to be in GB. G here stands for geometric mean. The non-negative Bernstein was non-negative coefficient. GB for geometric mean. And why do we call it that? Because we still require that the first and last control points are bigger than 0. In fact, the first and last control points are the values of the polynomial at the endpoints. So those definitely have to be bigger than 0. And then we change the requirement from P1 and P2 bigger than or equal to 0 to P1 and P2 are bounded by some constant times the geometric mean of their neighboring control points. The advantage of something like this is clearly that we can compute P0 times P2, in P2 plus in a couple flops. These whole operations are computed very quickly, as opposed to solving a program. And this condition wouldn't be very useful if it didn't imply that the polynomial is non-negative. So the theorem says two things. It says that every polynomial you can show is positive by this classical non-negative Bernstein method of taking in the control points and checking that they're non-negative. Every polynomial that has that you can prove with that property is non-negative with that property. You also would get is non-negative with this property. It contains the set of MB. We also have that every polynomial that's in GB, so every polynomial that satisfies these four inequalities, must be positive on the interval, or non-negative on the interval. Sorry, sometimes I'll say positive. For this whole talk, I mean non-negativity. So we claim this in the slide, but let's take a look before we go into any proofs of sort of what do the sets look like? Do we actually gain something by using these conditions? So again, we're, for the purpose of this section of the talk, just looking at cubic polynomials. Cubic polynomials have 4 parameters, and we want to look at 2-dimensional pictures. So we pick a 2-dimensional slice that makes sense. We fix the first and the last coefficient to be 1. And we let the P1 and P2 vary. And we ask the question, is P in NB, is P in GB, or is P in P? Again, NB is non-negative Bernstein, GB is our new condition, geometric Bernstein, and curly P is just the non-negative polynomials. Okay, so every point in this plot represents a polynomial, and we shade a point if it belongs to the set. So the condition that a polynomial is in NB is precisely that its Bernstein coefficients are bigger than or equal to 0, and so we shade the first quadrant. This shouldn't surprise anybody. So now we added onto this picture the set of things that we would prove are non-negative with these geometric Bernstein conditions. You see how many more polynomials become positive when we relax those 2 middle inequalities. Now, it is immediately clear that the set isn't convex, which is a disadvantage to this new condition. But if we add the graph of the set of polynomials that are non-negative on the interval 0, 1, we see that you actually get very close and asymptotically match the behavior of the set of positive polynomials. So this curve here that defines the boundary of P is a discriminant curve. It's a cubic discriminant curve. And the conditions for GB that define the boundary are quadratic curves. So there's really no way to completely match the behavior of that P with a quadratic boundary. Okay, so I hope this picture convinces you that it's at least worth looking at the set. There are a lot of polynomials that we can gain with a very simple condition, and we don't have to solve a second-order cone problem anymore. We can just, explicitly check the polynomials, the coefficients. Now, for illustration, we'll do the proof for the cubic case, but actually, very similar proof works for the whole arbitrary degree, and we'll talk about the matrix case, but the core idea is really the same idea. So it's a very nice illustrative proof. Remember, so the top of the slide reminds you that curly P is P non-negative on the interval. We want to show that every P that satisfies our conditions is non-negative on the interval. So the first big equation is just an identity. For any A and B, you can write the PI BIX sum as this messy thing. But what's important about the messy thing is that if there exists any A and B such that those two matrices are positive semi-definite, then you've proven that the polynomial is positive. So the A and B cancel in the expression on the right if you expand everything out. But because x is between 0 and 1, the first term, the x is non-negative, 1 minus x is non-negative, and then those quadratic forms are non-negative if the matrices are positive semi-definite. So we make this choice of A and B, and we claim that with this choice of A and B, that guarantees these matrices are positive semi-definite. We get that the traces are positive by the condition of P being in GB. So the geometric mean condition literally is that, that trace is non-negative. And the way that we chose A and B here make the determinants always non-negative. So trace and determinant non-negative on 2 by 2 matrix is enough for positive semi-definiteness. So actually, what we did was we chose an A and B, and we picked sort of the best A and B you can use in some sense. And that is our GB condition. And we'll talk about exactly what I mean by picking the best A and B you can pick. Okay, so now let's go to the more general setting. I'm just going to state the problem in that setting and then tell you what the generalization is. We're not going to go into the full proof there, but I should at least illustrate that it is a very natural and straightforward generalization. So first, what is the matrix polynomial in this case? So we let P of x be some combination of symmetric matrices. So the Pj are going to be symmetric matrices. And the Bjx's are the same Bernstein polynomials from before. But now instead of going from just 0 to 3, arbitrary degree goes to d. And then we can think about this. For every value of x, we get a matrix that's d by d. And we can compute the eigenvalues. So the plot below is just some random matrices, just to show you, you can just compute the eigenvalues. This is a well-defined object, the matrix polynomial. And we're going to ask the same question, which is, can you give conditions on the Pj that imply that the matrix is positive semi-definite on the whole interval? So can you prove that the smallest eigenvalue on that graph before is bigger than some amount, bigger than 0? Just as before, there's sort of the spectrum of conditions that you can give. You can write an exact, I'm going to call it expensive semi-definite program. Or you can do something a little cheaper and just compute the eigenvalue, or determine if each of the PIs or PJs are positive semi-definite. Right? The BJs are non-negative, and so any conic combination of the PJs is also non-negative. And so that would imply that that P is positive semi-definite for all x. And again, we ask the question, can we put something in between? And we're going to have the same answer. But first, we have to talk about the geometric mean. So when I said we picked the best possible A and B, in some sense, that's like given scalars h and k, we want the largest j such that this matrix is positive semi-definite. And if you're interested in this and you go back after, you'll see it's exactly sort of the condition that we needed was that this matrix is positive semi-definite, but we get the most new polynomials if we pick the largest j. So it turns out that if you ask this question of matrices H and K, you get something called the matrix geometric mean. So you might think of generalizing the geometric mean by just doing like capital A times capital B to the 1/2. Turns out this isn't symmetric, it has really no properties. But there's a nice answer to this question with connections to Riemannian geometry, applications all over the place. If you just start searching around, there are connections, everything that can be related to Riemannian geometry and positive semi-definite matrices, you can tie back to this. And at the bottom of the slide, I have the definition of the matrix geometric mean, or one possible definition. It's not immediately apparent that this definition is symmetric, but it actually is symmetric, unlike the AB to the 1/2. It's also not exactly how you would compute it, probably. There are more efficient ways of computing it, but this is sort of suggestive of the connections to Riemannian geometry, that it's the midpoint of a geodesic connecting the two PSD matrices. That's where the 1/2s come from. Okay, so the condition in the general case, just like we used, I said, the projection onto the non-negative orthant before, x plus was the maximum of x and 0. Now we project x onto the positive semi-definite cone. And we'll say that P is in the geometric Bernstein set if for all 0 between I and D, we lower bound our matrix coefficient, the coefficient matrix, by the geometric mean of the projections of the neighboring coefficient matrices. Okay, I don't say this on the slide, but P, like -1 is just 0, so you just still need that the first and the last, and so P, D plus 1 should also be 0 in this condition. So you still need the first and last are positive semi-definite, but as you go through all of the conditions, you just check the neighboring control, the geometric, you compare to the geometric mean of the control points. And I didn't write alpha I on the slide just because it's, I thought, maybe unnecessary clutter. It's a very simple expression we just know the answers to. It's some relation on binomial coefficients and some 1/2s depending on if you're on the endpoints. Once again, the important theorem is that everything that you can show is non-negative with NB also satisfies these conditions. And then these are bona fide certificates of non-negativity. Now I'll show you some, let's say, brief numerical experiments. So if we want to talk about how well this does, we should plug it into maybe a simple application or a simple pipeline that people might use for this. And so I'm going to talk about subdivision, explain it, just simplest possible example. So suppose you want to prove the polynomial 1 minus 2x squared is non-negative. Let's think for a moment of this polynomial as a cubic polynomial. So you can write it in this Bernstein cubic basis and get 4 coefficients. I plotted the control points. They're not all non-negative. So what we do is we subdivide into 2 polynomials, one on the interval 0 to 1/2, the other one on the interval 1/2 to 1. Then we rescale the polynomials to the intervals 0, 1 with the same shapes. And we get 2 new quadratic polynomials, which we again interpret as cubic polynomials, and we wrote the control points on the slide, or we plotted them. These are all non-negative. So we weren't able to prove that this polynomial is non-negative with the NB condition, but if we subdivide one time, then we can. And so we're going to, okay, so how do you subdivide? Well, there's this very nice algorithm called de Castelgeo's algorithm. In the very simple cubic case that we're talking about right now, explicit matrices that would compute them. But they're non-trivial. It's not like subdivision is totally free, and that's sort of the point, that if we can save in subdivisions, it does help. So the first experiment that I want to present, which might be the only one, is that we vary our parameter t, and we want to show that x minus t squared is bigger than some lower bound. And so we'll show it's bigger than by some lower bound, but then by adding the lower bound to the polynomial and showing that's not negative. And our steps are going to be to write this in the cubic Bernstein basis, and then keep subdividing and checking if NB, if checking the termination criteria. So this is a sort of interesting plot. Each point on the x-axis is a different polynomial, and the values on the y-axis are how many subdivisions it took to prove this polynomial is non-negative with each of the two methods. So for instance, when t is 1/2, we're talking about the polynomial x minus 1/2 squared, and right, they both take one subdivision to make this work. The important thing, that I think the nicest property of this graph, that shows, is that the NB condition is very sensitive to the location of the root. If you perturb like 1/2 just a little bit away, it actually might take maximal number of iterations. Whereas in the GB case, it's less sensitive to that location of the subdivision versus the root. Okay, and then I think that's all. Thanks.
Thank you, Mitchell. So, any questions?
It's a quick question. Can you do optimization with this?
That's a good question. You could do some optimization. You can't use like a convex optimization solver with it. But yeah, we're still working on ways to actually incorporate the optimization techniques.
Any question?
Thanks for the talk. Is there a natural way to create more certificates so you start filling the full set of positive polynomials?
Yeah, so we have other conditions that actually capture the other region, but it doesn't contain all of the NB. So if you start moving in, then you start losing things on the outside. And so I guess you could create some sort of hierarchy. The reason that we didn't really pursue that was because we were concerned with how expensive it was to compute this. Because if it's the discriminant is not that complicated to compute. So, but it's an interesting question of, is there an explicit hierarchy? Right now we just have like several different conditions.
Thank you.
Thanks. Can it be used for non-polynomials? In the sense that you can approximate a non-polynomial via Bernstein polynomials, but it's really most well suited. I guess you can use like, if you use this for splines, then you can use like a spline for your bigger function, and then for the splines you can show something with this. And that's actually maybe one of the main applications of Bernstein polynomials is for splining.
Okay, so we are running out of time. So thank you, Mitch, again.